Welcome to the pre-recording of the second half of Lecture 7 in the middle of the third week of the 8-week summer course on computer algorithms. In the first half, we introduced three greedy algorithms to compute spanning trees of connected graphs. We did not specify the data structures. So implementing an algorithm in this course means that we have to specify, and specifying means defining the operations in sufficient detail and their costs so that we can verify that the algorithms are efficient. So one of the algorithms, Kruskal's algorithm, added edges in increasing costs. So that meant that we could have several disconnected components and that we have to somewhere figure out how to merge them at the end, because we have a spanning tree that is a connected graph with no cycles. Okay, so we are going to introduce the union find data structure. That will be a very good data structure to manage a set of connected components that evolves. And with that, we can then prove the running time of Kruskal's algorithm. Towards the end of this pre-recording, I will briefly mention priority queues. Priority queues are in standard topic of data structures. And with priority queues, we will implement Prim's algorithm. Prim's algorithm works vertex by vertex, not edge by edge. Okay, so here is the problem statement. We are adding edges. Every edge has a cost, although for this part of the lecture, the cost, whether the graph is weighted or not, doesn't really matter. So the order in which the edges are added is determined by their cost in increasing order. Each time we need to find when we are, so the edges are sorted, no problem finding which edge, but we need to define an efficient data structure. So efficient means that in constant time, that's the best way, we need to find whether two components, if we are going to adding an edge, are these two vertices in the same component, or if not, how do we efficiently merge them? So the pseudocode probably says it better than I did in words. So we want to add an edge. We find A and B. A and B are the names of the components to which U and V belong. If those names are the same, then that means that U and V belong to the same component, and we can just insert the edge into that component. Otherwise, we have to take the union of the two components. Okay, so what we will define is a union find data structure. We will initialize, make such data structure for a given set of vertices. The given set of vertices will be considered as just as many isolated points as there are vertices. So for each vertex, we have to quickly define the name of the component which contains that vertex. And then if we have two disjoint components given by their names, we need to change the union find data structure so that A and B are merged. So these are the three major operations we need. What will we choose to implement? Well, we know how many vertices our graph has, so we can fix an array that has the advantage that the find runs in constant time. Perhaps I should not rush ahead. So what is in that array? For every vertex, we store the name of the component to which that vertex belongs. So then arrays have the advantage that to access any element happens in constant time. The making runs in linear time, so if we have yet no edges considered, then our union data structure represents disconnected components as many as we have vertices. So the choice of this array with what are the indices, what are the data elements that are represented, stored by this array, we have already defined two of three operations. The union requires a little bit more work. So here, just an example on how this data structure also evolves. At the left, we have 5 vertices. We have 5 vertices initially in an array of size 5. We have 5 different names. We could call them A, B, but call them 1 to 5. And what we do is we merge the last the last 2, and then the last 3, the last 4, and finally everything gets merged. So this is the illustration of the union. Okay, so why do we have to be a little bit more careful with the union? Because like in the previous example there, if the cost of the union could become linear in the number of vertices. So, and in order to prohibit this, we will label, so we have two disconnected components to begin with. We will maintain an extra array size, which keeps for every component the size. And we will change the labels only of the smallest component. So not unlike this example here. So I should have had indicated that here what we each time do, it doesn't matter when we do this the first time, but here you see that we change the label of the largest component. So, and each step already, if you are at the half of the set, the upper bound is actually in each step of the merge is actually the total size. So we want to prevent this, and here is one way to do this. So the pseudocode probably says it again better than I can say in words. We compare the sizes, and then we change the labels only of the smallest components. So the name of the component is the name of the largest set. So that means that we don't really update the size. of the labels of the largest set. It's not clear that this is any better because it's not obvious. It needs an argument, it needs a proof. So the unions, if we have a sequence of k unions to do, then this takes in total k log k operations. So how does this argument proceed? So in each union, we consider a different pair of vertices. So union takes the name of the largest set. So the size of the set that contains the vertex that we considered doubles. So the largest set after k union operation has therefore at most 2k vertices. So if you then check how many times we have the name of the component updated, well, this is as most the 2 logarithm of 2 times k. So at most 2 times k elements are involved in the sequence of union operations, and that happens at most the logarithm, the 2 logarithm of 2k. So for k elements, for k union operations, we have the k log k cost. Okay, let's consider an application of this. So earlier in the course, we considered graph traversal algorithms. So that was actually how we got started with working with graphs. List all the elements in a graph. We did this with breadth first, depth first, and then we said, look, an application of this is to compute the number of connected components in a graph. So we actually did not really expand on this or elaborate on this. If you were to do this, then you may also want to find for every vertex in the graph to which component did it belong. So here you see the problem specification. So for a graph, and now actually it should be considered a collection of different connected pieces. Write the algorithm for this and use the union find data structure to actually compute this. So what this exercise actually asks is that you run the graph traversals, whatever you want, depth first or breadth first, and you are, as you visit more and more vertices, you are going to update your union find data structure. Graph traversals take n plus m, have that as an upper bound, for one connected component with n and m. So the n and the m, if you have k connected components, separate this into k different n's and k different m's, where the n sub I counts the number of vertices in the ith component, the m sub I counts the number of edges in the ith component. So that's an application of the union find data structure to compute in a graph a structure that will tell you how many, for which in which component every vertex belongs to. Okay, let's go to Kruskal's algorithm now, our first major result. So the Kruskal's algorithm is going to insert edges according to their costs. The edges are sorted along their increasing cost. So we have m edges, n vertices, and we will show that the worst case running time is m log n. So they are sorting. So the sorting is actually the pre-processing step. This takes m log m. It's already kind of strange. We have m log n, but how can we get that the m log n? Well, in a completely connected graph, we can have no more than n square edges, or actually it's about the half of that. So the m square is an upper bound. So if you take the logarithm of n square, you have twice the logarithm of n. 2 is a constant, so in the big O, this disappears. Okay, so the initialization doesn't really, so the initialization already hits that bound. Now we have to show that we will stay within that bound. So for every edge, we will apply this find. The find is just done as many times as we have edges, or actually twice. So we do it, we may do it at most 2 times m. So this is where we have this cost O of m. So we have to do the union of for each edge. So we are working with a tree. So the Kruskal's algorithm will insert n minus 1 edges. And here we now had the property of the union find operations, that this operates in n log n. Okay, finally, we assumed that we had a connected graph, so m is at least n minus 1. So in this n log m, n log n, we can replace the n by m. That's an upper bound. So we don't do this both ways, but we do have the m log n worst case upper bound, which is the running time for Kruskal's algorithm. Okay, that settles the cost of Kruskal's algorithm, which is therefore an efficient algorithm, runs in polynomial time, and actually the bounds are very good. With Prim's algorithm, we have a vertex-oriented algorithm for which we will store the vertices along their attachment costs. So we have a priority queue that is used to store the keys of our these costs of our vertices. So what is a heap? A heap is a complete binary tree where the root is the most important or largest element. The subtrees are also heaps. So in every subtree, you do have that the root is also the most important element, also has the highest priority. If your priorities are given by numbers, then you can do this as a max heap when you look for the largest element that is at the root, or if at the bottom of the root you have the smallest number, the lowest priority, you have a min heap. If you sort in increasing order. So here we will sort along attachment cost. So we will have a min heap. The root will be the vertex with the smallest attachment cost. Okay, some more terminology. The root is called the top of the heap, and the bottom is the least important, and that's at the rightmost element. That's the deepest level of the tree. So in some sense, the notion of a heap in computer science, we draw trees kind of backwards. The root is always on top, but here it represents really a heap. Okay, how do you store a heap? Well, we can store this with an array. So this is a summary of what I once taught in the data structures course. I go very fast, so the book has a much more elaborate um, discussion on heaps in chapter 2. In this course, we skipped over it. Basically because we actually did not need it at that time. Now is a good introduction. If my description of a heap is not extensive enough, if you have forgotten everything about the heaps from your data structures class, then that may not be enough here. But I hope to illustrate with this example here. So here you see a max heap. The largest element is on top. You have two sub heaps, and you also see that the largest element there is each time on top. So what matters is that we kind of keep the information in an ordered way. What we need to have is that in each time we can very quickly get the most important element from the heap, and we can also update efficiently. So this is why this heap is complete, or well, a complete tree. So it's very well balanced. So the depth is logarithmic in the size of the numbers. How do we store this tree now? Well, we can store a tree via an array, as many, so that saves us pointers. So the convention is that since it is a complete binary tree, we can quickly find the child via an index calculation. The left child, and you can see this here, so here you see the indices. So you take the index of 90, 2 times 0 plus 1. You can also do this for 1. 2 times 1 plus 1 gives you 3. This gives you actually the position of where 21 is in the array as the left child of 65. So there is very efficient arithmetic that can be done in the representation of a heap, optimal storage, and also very quick to navigate. So typically when we navigate, we go from the parent to a child, or from a child to a parent. And when we insert, we swap parents with children. So again, this is very short. So if you are in a data structures course, the best sorting algorithms are also covered there. But the sort that is determined by the data structure, by the heap, is actually heap sort. So what happens is that in a heap sort, one pushes a sequence of items to the heap. You push it to the bottom, so the heap grows from the bottom, and you maintain the property of the heap. So the root is the most important one. So, and also this is property in the subheaps. So which means that if, as long as the bottom element, as long as there is an element out of place, if the new bottom element is actually larger than the parent, you swap that bottom with the parent. Then on that spot, you also check you now have a new element, which was at the bottom, which is the element that you inserted. You also compare that to the parent. And it might be that if your sequence is already sorted, that not much needs to be done. But at most, logarithm of n operations need to be done when you do a push or when you do a pop. The pop is symmetric. When you remove the top, you're going to replace it with the bottom, and you're going to swap that bottom. So you're going to actually reinsert the bottom in when you pop. Okay, this is an important theorem, an important result, which shows that heap sort runs in n log n. So I will not prove this theorem. Again, look at your data structures courses. So let's now see how we can implement Prim's algorithm with a priority tree. So we have already a set of vertices, we call it S, that are attached. Now for all the other vertices, so in the first step you have one vertex, and for all the vertices that are connected to that vertex, you have the length of the cost of the edge, and that will be the key in that you insert in your heap. So each time when you attach a vertex, then it has to be popped. So you no longer consider that vertex. So you pop actually that element and with the smallest value. Popping it means that you restore the property of the heap. That takes a cost logarithmic of n. So after this popping, you have to consider all the edges that are connected to the vertex you popped. And you have to insert, so now you have more vertices that can be attached. So you have to insert also all the vertices with their costs. So the value alpha width in the context of Prim's algorithm is the cost. So you are inserting, but also you are changing. So you have to recompute for, so some of the vertices that could already have been attached, this may change because they are connected now to S in a shorter way. So we executed Prim's algorithm on site. So the advantage of spelling out the data structures means that we very carefully have to investigate what the smallest attachment cost means in every step. Okay, so then our second main result in the second half of this lecture is that the worst case running time of Prim's algorithm is actually the same as the Kruskal's method. So let's examine how this goes. So we have n-1 steps. Again, any tree on n vertices has n-1 edges. So we are done actually after adding those n vertices. So we do an extract min. So each time when we select the vertex with the smallest attachment cost, so that's actually the gives you the n log n cost. But then we have the edges that we have to consider. So for every edge, we have to change this. So the difficulty in this argument here is that the algorithm is vertex oriented, but in examining the costs, you have to take into account that we will do the change key only at the moment when we are starting to add the vertex that appears in this edge. So, and that change key costs logarithm of n, and we have m edges. So this is how we get to the m log n costs. Again, our graph has at least n minus 1 edges because it's a connected graph. So therefore, we can bound the n in the n times log n by m. We do this by m log m. Okay, so the total cost therefore is proven. So in order to do this proof, we have to understand the priority queues. Now, one last exercise. So we ran Prim's algorithm in the first half of this pre-recording, or it is in the slides. Now, what you should do, we had only 7 vertices, so you should make a heap and illustrate the evolution of the heap for all the steps of Prim's algorithm. So 7 vertices, 6 steps, so you have 6 steps that show the evolution of the priority queue. So this is another good exercise to get reacquainted or to understand better the role of the data structure, the heap, in this algorithm. Okay, I hope that this lecture was interesting and that you have an idea on how to start the exercises. We are concluding our investigation of greedy algorithms. So closing a chapter in our textbook. So it's also now a good moment to read the textbook and also check there the arguments and the extra exercises that you can find there.